As you know, mathematics is a science of quantity, right? And quantity can be discrete or continuous, what opens the way to divide mathematics in two branches: arithmetic and geometry. Arithmetic is deals with discrete numbers, right? As you know, and geometry with a continuous quantity. The continuous quantity is understood by means of discrete quantity. That's a big problem, metaphysical problem, but I cannot, maybe I have no time to discuss this. And there are algebra also, but what is algebra? It's very hard to give a definition, but I think algebra deals with some sophisticated and very abstract structures behind arithmetic and geometry. So you can find people working on algebraic geometry and so on. So we are talking about quantity. Let us focus on arithmetic, the discrete quantity. The first type of numbers are that I wanted to show you. These numbers are very intuitive. They are the natural numbers. It's difficult to imagine someone that doesn't know what are the natural numbers. 1, 2, 3, 4, 5, and so on. 1 billion, it's also a natural number, right? So we define the set of natural numbers as the infinite numbers. It never ends. Okay? 1, 2, 3, 4, 5, 6, 7, and it has not a final number. Every number you say, you can add number 1, and you will give and you will have the next number. There are always the next number. That's a very non-trivial property of this set, the set of natural numbers. Observe that this set can handle with all kinds of discrete quantities. Or no, maybe not. I don't know. At least for now. That's why this set received this name, the natural numbers. They are not unnatural, right? But now let me say something which an example that I gave it in another lecture, but that's a very important example to explain the nature of the quantities. What is quantities at all? You imagine 5 cats, 5 dogs, 5 horses, and 5 whales. What do they have in common? Of course, there are many things in common. For example, they are living beings. They are not inorganic. They are animals. They are not plant, and they are all mammals, right? Let's remember that the whale is not fish. It is a mammal. Okay. But if we imagine more 5 crocodiles and 5 chickens, all these sets of 5 elements still have many things in common, but less than before, right? Because the crocodile is reptile and the chicken is a bird, or at least similar. They are not mammals at all. So if I add 5 more sets of 5 elements, the things in common tends to decay, right? I think you are understanding. And adding a lot more will, as I said, will make difficult to find out a common feature. But as far as I've add 5 things, always 5 things, always the sets of 5 elements, we will have always a single limiting thing in common, which is the right 5, the quantity 5. That's right. That's the limiting thing that remains always in common between every a large number of 5 elements, right? So the quantity is the last genus, in Portuguese, gênero, the last genus that fits every group, every group. Only if you choose a set of 6 elements, okay? But let us suppose that we have a large number of sets. All of these sets will have 5 elements. You may not find anything in common, but you always find the 5, which is the quantity. So we can forget all genus and species, which define the things, like mammals, like fish, like anything. But we'll have still there remaining a common thing remaining, which will be the quantity itself, the 5 in this case, right? That's why we can reproduce here this result, which was very well known by scholastics, by Aristotle, and so on, which is the quantity is the first quality that inheres on prime matter, right? Or I could say also in different way, more original way. The quantity is the first accident or the first accidental formality that inheres on prime matter, right? Because there are the duality, matter and form. I explained this thing in another lecture, but the matter is a principle which gives the possibility to exist, and the form is the existence and act of that is a concretization of that possibility. The possibility, for example, clay can or cannot become a sculpture. Okay, the sculpture is the form, and the clay is the matter. Okay. there are representative elements that represents these two principles, which is matter and form. And what I am saying right now is that the quantity, no matter discrete quantity or continuous quantity, but the quantity itself is the first accidental form that inheres on prime matter, which means that the quantity is just quite very close to pure matter, to prime matter, right? Now, this set of natural numbers can deal with discrete quantities. That's nice, but people created more sets. The integral numbers or integers, I just cannot pronounce this word. It's very difficult. Integers, which I represent by letter Z, and the letter Q represents the rational numbers, and the irrational numbers by letter I, Y. Y? Well. And the real numbers, or reals, are defined as the union between the rational numbers and irrational numbers. There are more sets, more non-trivial sets called the complex numbers, and one more, if I am not wrong, the different with three different imaginary parts, which is quaternions, but that's not the subject for discussing here. Let us stop. It is enough to consider just until the rational numbers, right? The irrational numbers, the would be another chapter, would be another talk, and that's would take much more time. Okay. But let us define the integers. The integers is the natural numbers plus their negative counterpart. Just that. You can, of course, you can define formally defined, but we basically it is formed by all natural numbers plus the corresponding what we say is the symmetricals, and the symmetrical numbers. The symmetrical of number 3 is the number with such that if I add this number to 3, it will give 0, which is some another element that I can define such that the operation already defined, which is the addition, if we add this neutral element to every number, we will give the same number. That's because it is the neutral element. But this is, I think, these formalizations are not necessary at all. It's enough to understand the idea. Every person have the correct idea. What is the integral numbers, which is infinite, not to just to the right, but to the left also, right? That's okay. Different authors can define in a way slightly different from me. There are, maybe you can include the zero number in the definition of natural numbers, I don't know, but that's irrelevant for our purpose, okay? An important remark, the set of natural numbers n has infinite elements. What about the set Z? Of course, it has infinite elements also. That's obvious, right? But to answer this question, the mathematicians defined a concept called cardinality of a set as the number of elements of a set. The cardinality of a set of 5 cats is 5. The cardinality of a set of all of the students which is attending my lecture is maybe, I don't know, maybe 20 or 30, between 20, okay, let's say 25 or 23. That's the cardinality of the set. But the cardinality for infinite sets, that's subtle. That's a little bit more sophisticated. This definition doesn't work because the infinite sets, how many elements the natural numbers have? Infinite, and infinite is not a number, right? Thus, cardinality can be extended to infinite sets by redefinition, the following redefinition. Two infinite sets have the same cardinality when there is a bijection between them. Now, the bijection is any relation between one element of one set and another element of another set, in such a way that there are no elements out of this relation in both sets, and the one element is related to another unique element and of the other set, and in the other set all the elements are related back with just one element. So that's very, I just decided not to write these all bullshits here. I'm sorry about the words, but they're important. For formalities is very important, but I'm trying to explain this for common people, maybe some people who doesn't know well mathematics. So I decided not to write big formalities here, but I can explain bijection just by showing figures. Let us see. In the left figure, that's not bijection, because you have this element here in the middle is related with two elements, and bijection, the relation must be one-to-one, right? And in the picture in the right, there is not a bijection also, because we have an element here which is out of any relation, right? So that's not a bijection. And another more 3 examples. If you try, before I say, try to classify the left picture, the middle and the right picture. Which of them can be considered as a bijection? Try to do this. You don't need to speak, but if you want, go ahead. Can I say? The middle is a bijection, in your opinion. More people have more different opinion. Please don't be afraid. If you made a mistake, there is a very modest fine of $50. I'm kidding, okay? I'm kidding. The right, yes. Because in the middle we have not one-to-one correspondence. There is, okay, you see now. And here is missing. This element here in the left are out from any relation. It's alone. And every element have a correspondent, unique correspondent, okay? And every element in the right, the second set, will have also backward another element. So that's clearly now it's clear that the right here the right picture tells us about that's a bijection. One-to-one, this related to this element is related to this and this and this and this. Nobody is missing. Okay, that's okay right now, people. Everyone. So that's a bijection, right? Great. Not bijection, not a bijection. That's a bijection. Does the set of even numbers has the same cardinality of the set of natural numbers? Because there is a bijective relation such that for each element of the even naturals, a unique element of natural numbers is associated. And there are no elements of the natural numbers left out. That's a representation of this bijection, of this relation. We take, for example, n is the natural numbers. We are relating all the elements of even number in Portuguese is a número par, okay? 2, 4, 6, 8, and so on. So you think this set, the set of even numbers. This set has the elements 2, 4, 6, 8, and so on. And for every such an element, I can associate the natural number. Like this. I can associate the 2 with the number 1. The number 4, I can relate it to the number 2. The 6, the number is related to number 3. The number 8 is related to number 4, and so on. The number 3,572 is related to number 1,786. A difficult task to say it in English for me. And you can, there is some need to show you that the first 1 billion numbers, elements, the first 1 billion elements of this set, they all will be in bijection with the first 100, half billion maybe, of natural numbers. I cannot, because we have here the first 3 even natural numbers is 2, 4, and 6. The first 3 natural numbers, 1, 2, 3, right? The first 4 of even natural numbers are the following: 2, 4, 6, 8. And the first 4 natural numbers are in bijection with the previous set I defined. But if you extend, you can extend this set to infinite, to all the even natural numbers. And will be a bijection between this infinite set to another infinite set, which is the set of natural numbers. Right? I think it is easy to see that, right? Thus, the cardinality of even numbers are the same. Is the same. Thus, the cardinality of even number is the same of the cardinality of the natural numbers. What seems a contradiction, because the even numbers are part of the natural numbers, right? So a part of natural numbers, it's half more precisely, has the same number of elements of the whole natural numbers. Okay, but that's not completely true, because the set of even numbers does not have the same number of elements of the natural numbers. It has the same cardinality, right? So that's a mistake here. Not so bad, right? The things are not so bad. It has the same cardinality, not the same number, right? But before elucidating this, let us focus in the other set, the set of integers. This set has also the same cardinality of the natural numbers, okay? Unfortunately, I'm not explain and prove it is here, but I just ask you for believe me that this set has also the same cardinality of the natural numbers, right? But I give just an argumentation to see that the cardinality of integers are equal, the same cardinality of the naturals. Observe that all negative numbers have the same cardinality of the odd numbers, and all positive numbers have the same cardinality of even numbers. Okay, that's just a way to facilitate, to clarify. But let me say a more striking affirmation. The same occurs with the rational numbers. The set of rational numbers is defined as containing all the numbers in the form integer number over another integer number, such that P, Q, and Q are both integers without any common factor. For example, 7 over 3, that's a rational number. The number 7 itself is also a rational number. It is also a natural number, it is an integer number, and it is also a rational number, because the number 7 or 6 here, right here, the number 6 can be written as in this form, 6 over 1. And 6 have any common factor excepting 1. The 6 can be written as 2 times 3. Okay? That's no one factor. So the 6 is a rational number. Every integer number is a rational number also. This number here, written as a periodic, I cannot say in English, it can be written also as a fraction, right in this way. We have 133 over 99. And this number is also a rational number, right? And so on. Of course, this 12 over 2, they have common factor numbers, but it can be expressed like this one, okay? So I will say that it is possible to define a bijection between both sets, the rationals and the naturals. Okay, it's very hard to believe. I know that, but I cannot prove it right here. If you want some proof, there is a lot of proofs in the internet, and you can see or ask me after, okay? And just believe me. The rational number has the same cardinality of the natural numbers. So it happens that the set irrational has not the same cardinality of natural, because it is a very different kind of infinity, because it has so big quantity that are irrationals. So, but that's not the subject for this talk, okay? Unfortunately, because the subject is very interesting. Maybe another talk. Maybe next year. To say a set A has the same cardinality of the natural numbers is to say that the set A have infinite elements, but this infinite is enumerable. So you can say the set A is enumerable. Okay. So you say that a set is enumerable with, there are two possibilities. Possibility 1, it has the same cardinality of part of natural numbers, or it has the same cardinality of the natural numbers, the whole natural numbers, if it has infinite elements. This is so because a bijection is just the counting process, right? Remember, we did the bijection. The bijection is, by a sense, a counting procedure. We are counting how many apples are there in this bag. How is it? This is bijection. Every time you count 1 apple, 2 apples, 3 apples, 4 apples. There are 4 apples in front of me. When I did this, what happened here? I did a counting procedure which I established, not in a formal way, but in an informal way, a bijection between these 4 apples and the set 1, 2, 3, and 4 apples. But in this example, I used the playing cards, right? So when you count how many playing cards I have, you do a bijection with the set 1, 2, 3, 4, if there are 4 playing cards. And this bijection is bijection between my 4 playing cards and this set, right? The set of irrationals is so big that it is not an enumerable set. It's hard to understand this, but the infinity elements of infinity, the infinite irrationals are so a big number, or maybe not a big number, but a big something, right? Because that's not a number anymore. But the so big something that I cannot just to count. I start to count and I cannot count. Even if I had superpowers, let us suppose that I have superpowers that I can count every natural numbers. I can count it. But if I have in front of me all of irrational numbers, I could not count these irrational numbers, right? That's the situation, right? And just for illustration, just for fun, I give an example of an irrational number. It's the root of 2. The proof that root of 2 is not rational is summarized here. You can see everywhere in the internet much better explanation than that, okay? Let us prove by contradiction. Suppose that this irrational number is rational. So if it is rational, it can be written as in this form, and P and Q have no common factor. I mean, this fraction cannot be simplified. That's it. If we take both sides of this equation to the squared, so we will have this equation right here, P squared equal to 2 and times Q squared. And this means that P squared is an even number, because written in this form is a number times another number. This is even number, right? But the square of any odd number is also an odd number. So the P is also an even number, right? It's also an even number, because if it were odd number, it squared would give us an odd number also. But we know that P squared is an even number, so that's why P is also an even number. Thus, let us substitute in the place of P here in this equation. We can write in the place of P, we can write 2 times n. N is any natural number, because any even number can be written as the product of 2 times any number, any natural number, right? So we have P squared equal to 2 squared, and the consequence of this is that that equation, okay? 4, okay? And after we have the following consequence, the q over n, we take the square root of this equation, and we find the square root of 2 is equal to q over n. And this n is different from q. Okay? So that's a contradiction. So that's the proof by which we cannot write the square root of 2 like in this form. So the square root is not rational. Or I mean, the number whose square is equal to 2 is not a rational number, right? Okay, if you have some question, you can interrupt me, right? Before solving the paradox by which the part is equal to the whole, let us mention an interesting property of rational numbers, just to finish the talk today. The rationals are what people call dense in reals. I did not talk about reals, but imagine a straight line, right? If we take 2 points in the right, yeah, I can. You can write number 1, number 2, number 3. If you associate every natural numbers with some discrete points in this straight line, you can also put, if this is number 1 and this is number 2, so this number in the middle should be 1 over 2. Is there a rational number? So you can expect between natural numbers, you can put a lot of rationals, right? But it turns out that these properties that the rational are dense and reals. It means precisely that you can choose any 2 points in the straight line, and it will be, no matter how close one point is close to another point, but it will be between these points at least one rational. The consequence is that actually it will be infinite rationals between any 2 points you choose in the straight line, right? Just properties, just to maybe you don't understand clearly what I'm saying, but maybe you have some curiosity and see in the internet, okay? So that's the end of the first part, and tomorrow I will plan to give a much shorter talk, very few things, but I'm planning to talk directly the resolution of this strange paradox, the part equal to the whole. Okay, and that's the content I'm planning for tomorrow. Maybe I can speak about 20 or 30 minutes tomorrow, right? So we stop here, and I stop recording, right? So let's continue. Now let us see talk about those paradoxes I have mentioned yesterday. So let's turn back to the apparent contradiction in which the set of natural numbers have the same size of the set of the even numbers we have seen yesterday. That's not exactly the case. The set of natural numbers have the same cardinality of the set of the cardinality of the set of even numbers, okay, or the set of integers, or even the set of rational numbers, okay. So these infinite sets have the same cardinality. But this is very strange, even if after all it seems something not a little bit strange, okay. And in particular, any set with infinite enumerable elements has the same cardinality of the set of natural numbers, what I have said right now. All these infinities are the same. That's in the sense that the cardinality is the same. This is the basis of the Hilbert-Hotel paradox. Maybe most of you have heard about the paradox with the Hilbert paradox. What serves as the basis for the Hilbert paradox is the paradox in which the parts are equal to the whole. But in the chapter 7 of the book O Jardim das Aflições, I'm sorry because I don't know if this book has translation in English. The philosopher Olavo de Carvalho solved this paradox I think in one or two pages, by simply observing that all those sets are actually the same set. Just for you have an account about the Hilbert paradox. You imagine a hotel with infinite rooms, and suppose that all the infinite rooms are occupied. Then it comes let's say 20 people come to the hotel, and then the officer says to 20 people, well, the hotel is plenty, is full, but maybe I can arrange 20 rooms for you. And he asked for the first 20 floors, the first 20 rooms, to room 1, room 2, room 3, until 20. The officer asked the first 20 people occupying the first 20 rooms to occupy the 20 more rooms upside, and then the 20 people from outside get their rooms, right? That's the paradox. The set of natural numbers, whatever it is that's the solution, is identical to the set of even numbers, and also to the sets of odd numbers, and also the set of natural numbers is identical to the integers and to rational numbers also, and to any infinite enumerable set. All these sets we are talking about are the same, are just one set, right? Because the unique difference between these sets is an apparent difference. Because the unique real difference between these sets are the labels of their elements. Their elements have different labels. I can nominate the elements of any infinite set as 1, 2, 3, 4, 5, or just as 2, 4, 6, 8, or even as 1, 1 over 2, 2, 2 over 3, 3 over 2. That's the way I label the elements. That's how the sets get apparent difference between. So the proof of this is evident. The bijection is the labeling procedure itself, right? The bijection, which is the relation I establish between the elements of the set and the elements of another set. This is the way I label the elements of a set. Right? The set of natural numbers seems to be bigger than the set of even numbers because we never think all of the infinite elements as an actual reality. That's very important. We always compare, that's the way our mind works. Okay? We always compare a finite quantity of elements with a finite quantity of another elements. That's why the set of natural numbers seems to be bigger than the set of even numbers. For example, we compare all natural numbers from 1 to 10 to 100, and then compare with the even numbers from 2 to 100. Obviously, the set of even numbers are less, and that's no mistake by saying that, right? That's perfectly right. What is not right is when you say that the infinite set of all natural numbers are bigger than the set of all even numbers. Because all is a problematic here. The mistake is to deal with infinite sets as they were, as legitimate as the finite sets. And this is false. There are two different things which gain the same name, set. The infinite is infinite, is infinite, without end or without borders. The meaning of infinite in infinite set, when we say infinite set, can be then expressed by the concept of unfinished, which in Portuguese means inacabado. Right? So that's different from the unfinished symphony of Schubert, for instance. Because the unfinished symphony of Schubert is a symphony. As a matter of fact, it is a symphony, okay, which have an accidental difference between when we compare the unfinished symphony of Schubert with another symphony, for example, for the great symphony of Schubert, which is, if I am not wrong, the seventh, and the unfinished maybe is the 8th. But I saw discrepancy in this respect already. Okay, but okay. In this context, these infinite sets, the infinite is not a new or additional characteristic of something. That's very important here, what I'm saying right now. In this context, the infinite is not a new or additional characteristic of something, but it expresses precisely the absence of a normal feature which is present in everything normal. such as the set of 10 apples. That's a normal set. How can I say? That's a normal set. But an infinite set, infinite is not a new feature, but is the absence of desirable feature. I mean, with this I can surely say the infinite is infinitely less than the finite, right? Because it's precisely the opposite we always say, right? But I mean, quantitatively, the infinite is more than the finite. I mean, maybe more, maybe. I'm not sure right now, but okay, quantitatively we can say that. But ontologically, for sure, the infinite is less than the finite. Right? But what about the Hilbert Hotel? The set of rooms in hotel is very different from the set of 20 people that just arrived at the hotel. These two sets have the same name, the set. They are said to be set, but are things of different species, but different things. When the 20 people enter the hotel, they lose the superior status, which is the set with an actual number of elements, with the set with a definite number of elements. They lose this superior status and become a set with the status of having a non-actual number of elements, or if you want, a potential number of elements, potential, which is ontologically inferior status. Ontologically inferior status. So that's because infinite is infinitely less than finite. Right? That's the analog of a black hole. The 20 people are entering a black hole. The black hole is eating everything by gravitation, and eats everything, and everything that enters the black hole goes to nothing, right? Goes to nothing. So it is impossible to label infinite objects. We can always label the first 200, for example, objects, or 300. Thus, the labeling of 200 objects will be an act if we just I just label the list of the 20 objects. So that's the labeling of the 200 objects will be an act. And to label more 5 objects beyond those 200 will be a potency, is a potency. I just can label more, 5 more, I can label. So this is a potency, or this is power, okay? And I can decide to label 5 more or not to label 5 more. This is a potency. Then the infinite repetition of the labeling process is the extrapolation of potential realities crossing the limit of the potency itself. I can label 5 more objects, but I cannot label infinite more objects. I cannot do that. I can just imagine an extrapolation, but this cannot be an act, never. And this presupposes the existence of the quantitative infinity as an act. The quantitative infinity cannot exist in act. This is a metaphysical principle known by the ancients, which have been forgotten by the moderns, right? But the straight line contains, someone could say, but the straight line contains infinite points, right? So it is a quantitative infinity as an act, right? But that's false, because the continuum, or the straight line if you want, has infinity just in potency, in power, in the sense that it can be divided indefinitely. But you cannot see actually infinite points in this straight line. As a matter of fact, you cannot see infinite identifiable quantities of whatever, of corporeal subjects, of corporeal objects, whatever. Because that's a very simple principle. It's a apodictic principle. The quantitative infinity cannot exist in act, right? Let us prove this. I think that this does not need any proof at all, because it's an evidence. But I say evidence here, not in the English meaning evidence, because in English evidence means in Portuguese what we say by how can I say indício? Indício in English, I forget. It's I forgot the word. Because evidence, the gun is an evidence of the crime. That's the sense the evidence is used in English. But here I'm using the word evidence by something that does not need any proof, that you are completely sure. So I consider this that the quantitative infinity cannot exist in act an evidence. But let us prove this by the proof by contradiction, which is that we suppose it is true and arrive at a logical consequence which is contradictory. Suppose the quantity infinity is possible. The quantitative infinity is possible. Suppose that. Thus, imagine a Superman with extraordinary, I forgot the right here, okay, extraordinary ability. Oh, I forgot another, that is not the age. Imagine a Superman with extraordinary ability, capable of selecting any apple from the infinite apples in front of him. Suppose there are infinite apples in front of him, and he has the ability to select any of all the infinite. He sees all the infinite apples, and he have the power to choose just one apple. That's the supposition. Of course, the supposition is impossible, but for the purpose of the proving, it's okay, right? If there were just 2,000 apples to choose, the probability of choosing the third apple or just another one is exactly equal to 1 over 2,000. Is that right? But with infinite apples, the probability of choosing the third apple would be zero. Right? Okay. So that's the contradiction, and that's the proof. But let me do some observation about that. I would like to, well, about this particular proof, okay? I make some observation about this particular proof. Most of you didn't believe on the validity of this proof, and probably you are right. You are completely right. The reason is that the contradiction used in the proof seems to be silly. And that's silly, right? That's right. And childish. Besides the fact that lots of mathematicians have already thought about it. It did this for sure, right? So theories and ideas apparently cannot be that simple. Cannot be that simple. Because beyond some degree, maximum, let's say, beyond some maximum degree of simplicity, theories and ideas are usually understood as a rediscovery of the well, okay, or as a silly, outdated belief. So that's this proof seems to be something wrong. Okay, but maybe if you point somewhere, if you point the precise mistake done, please feel free to email me, right? I can give my email in the chat again, but okay, that's. Does the Superman cannot choose any apple at all? So just for concluding, what is a contradiction? Because this ability of choosing, as I said, his ability of choosing any apple depends on the mere possibility of the quantitative infinity in act. That's because I consider this a real contradiction, right? Okay, but I can, maybe this demonstration is have something bizarre, something wrong, but anyways, I would like to show maybe a possibility of a conjecture here. Observe that this proof is a way of solving the paradox by which it is impossible to choose one single apple. Perhaps that's just a conjecture. Who knows? Every demonstration by contradiction can be viewed as an instance of solving a paradox and vice versa. Who knows? I don't know. Maybe it's interesting to investigate that. So let us summarize the main ideas and results we have reached yesterday and today. The first, the infinity in mathematics is not an additional category, but it is an expression. It is the expression of the absence of actuality. In other words, the infinite is not a positive quality, but a negative one. This is the sense by which infinite is less than finite. And by the way, infinitely less. The second, the part is always less than the whole. This is always true. Don't worry about that, okay? Or, the set of even numbers is not part of the set of natural numbers, right? Because Olavo de Carvalho just showed us that these two sets are the same set, not different at all. And three, The existence of the quantitative infinity in act is impossible. Otherwise, it would lead to a contradiction. Is there a conjecture connecting any demonstration by contradiction to a paradox resolution and vice versa? Honestly, I don't know. Maybe not. I don't know. Right? Okay, thank you. I'm indebted with an indefinite number of references, books, authors, and people. So there's no sense in writing here some references, books, papers, because this is the resulting of many years learning from many books, many people, many, And I just mentioned a few of these influences. Of course, I cannot. There's no need to cite Aristotle or St. Thomas, right? And I'm in debt with many people like Olavo de Carvalho, René Guénon, Wolfgang Schmidt, Vincent Smith, Edward Feser, William Wallace, Rafael de Paula, and many others. Okay. Thank you very much. It was my pleasure to have this opportunity to giving this talk, and I acknowledge the organization of Global July, which who give me this valuable opportunity. Okay. Any question? I cannot. Okay, please. That's just an analogy. Every analogy have a lot of things that are completely different at all. That's the case, but just one or two similar. Because the people entering the hotel, after they enter the hotel, they will be elements of the hotel, right? And by doing so, they lose the set of an actual 20 people elements. This set lose the characteristic of having a definite number of elements. That's exactly the way that these 20 people goes to nothing, they are absorbed by an infinite set, which is a set with a missing property, which has a missing property. That's the analogy, because the black hole is maybe you have heard about that in media and so on, and the black hole is is a very gravitating, is an object predicted by general relativity, which has the property of the property is that every being that falls into a black hole cannot go outside again, even the light. That's why the name is black hole, right? So inside the black hole, there is in practice there is nothing, because everything inside the black hole cannot go up outside. So that's the sense that we can say that inside black hole there is nothing, right? I hope something more or less. Yeah. Yes, it can still grow in time. It grows, but it's a dark object, completely dark object, and maybe thinking right now, the analogy it, it appears to be more serious analogy because the dark is the symbol of maybe the one of the yang and yin, the Chinese wisdom, um, is the which symbolizes uh, the pure power or pure potency or pure unintelligibility. And the black hole has something like in this sense, which is black, right? And there is no every information is destroyed, somehow destroyed inside black hole. Inside black hole. So every intelligibility is destroyed inside black hole. So that's an interesting analogy, maybe better than I thought, right? Okay. Any more question? I just stop record.